Welcome, everyone. Today we are exploring a monumental shift in cybersecurity, AI-driven kernel-level auditing. With the arrival of Anthropic's Claude Mythos, we have entered an era where no operating system, no matter how hardened, is safe from autonomous vulnerability discovery. Let's get started. Let's begin with the what. Kernel-level auditing is the deepest form of security analysis. The kernel is the heart of an operating system. If it is compromised, the entire machine falls. For decades, this auditing required elite human experts. However, Anthropic's Claude Mythos preview has shattered this paradigm. Mythos is a frontier AI model capable of autonomously reading millions of lines of code to find zero-day vulnerabilities, flaws previously unknown to developers. During its evaluations, it didn't just target one platform. It found high-severity vulnerabilities across every major operating system, including Linux, FreeBSD, and OpenBSD. In one benchmark, it achieved full control flow hijack, meaning complete system compromise on 10 separate, fully patched targets without any human steering. This proves that AI is now a superhuman kernel auditor. Looking at this flowchart, you can see the broad, universal impact of Claude Mythos. The AI analyzes the core operating systems we rely on daily. It successfully targets the Linux kernel, achieving multiple full control flow hijacks. It targets FreeBSD, developing remote code execution exploits. And it targets OpenBSD, historically one of the most secure OSes, finding critical denial of service vulnerabilities. The architecture of modern computing is fundamentally exposed. To understand the basics, we must ask, how does Mythos differ from the tools we already use? Traditional kernel security relies on fuzzing. Tools like syscaller blindly throw millions of random data packets at software, waiting for a crash. But a crash is just a symptom. It is not an exploit. Fuzzers lack semantic understanding. Mythos, on the other hand, reads C and C++ code like an expert human engineer. Because kernels are built in these memory-unsafe languages, pointers and memory addresses are everywhere. Mythos understands the developer's underlying logic and intent. It can spot a gap between what the code is supposed to do and what it actually does. Where a fuzzer stops at a kernel panic, Mythos autonomously writes the precise proof-of-concept exploit code needed to gain root privileges. This diagram contrasts traditional methods with AI reasoning. The top path shows traditional fuzzing using brute force to cause a system crash, which then bottlenecks at requiring human analysis. The bottom path shows Mythos applying semantic analysis to discover logic flaws. It bypasses the human bottleneck entirely through autonomous exploit generation, leading directly to weaponized root access. This is why the speed of discovery has collapsed from months to minutes. Why is no OS safe? The primary reason is the heavy burden of legacy code. Modern kernels contain millions of lines of code written decades ago. Because these files have been audited by humans countless times, we falsely assume they are secure. Mythos shattered this assumption. It autonomously discovered a 27-year-old vulnerability in OpenBSD, an operating system famous for its extreme security hardening. The bug existed in the TCP Selective Acknowledgement (SAC) code written in 1998. Mythos realized that a specifically crafted TCP packet could simultaneously delete a hole in a linked list and trigger a new append, causing the kernel to write to a null pointer. This subtle logic flaw allows an attacker to remotely crash any unpatched OpenBSD machine. AI proves that obscurity and age do not equal security. Follow this timeline of the OpenBSD vulnerability. The code was written in 1998 and survived 27 years of human audits and millions of automated fuzzing tests. But in April 2026, Mythos analyzed the codebase. Using deep semantic reasoning, it found the subtle linked list flaw instantly. The result is a remote null pointer dereference. What humans missed for 3 decades, the AI found in a matter of hours. How does Mythos actually hack a modern kernel? It masters the art of exploit chaining. Today, a single bug is rarely enough to compromise a system. Kernels use advanced defenses like KSLR kernel address space layout randomization, which scrambles where code lives in memory so attackers execute blind. Mythos overcomes this autonomously. It finds a low-severity read vulnerability to leak memory addresses, effectively bypassing KSLR and mapping the system. With the layout revealed, it deploys a second write vulnerability, such as an out-of-bounds heap write, to change the data structures that govern user permissions. We have nearly a dozen examples where Mythos chained 2, 3, or even 4 vulnerabilities together to systematically dismantle Linux kernel defenses and grant itself root access. This sequence diagram illustrates autonomous exploit chaining. The Mythos AI initiates bug 1, an out-of-bounds read, causing the OS kernel to leak memory addresses. The AI computes the KSLR offset internally, de-randomizing the memory. It then executes bug 2, a heap spray to align memory structures, followed immediately by bug 3, an out-of-bounds write. The sequence culminates in the kernel granting root access. The AI orchestrated this entire attack path natively. Let's deep dive into how Mythos handles hard technical constraints. Understanding a vulnerability is easy. Engineering a payload to fit into a restricted memory space is incredibly hard. Mythos autonomously exploited a 17-year-old RCE flaw in the FreeBSD NFS server. To gain control without injecting new code, it built a return-oriented programming, or ROP chain. The problem, the required ROP chain was over 1,000 bytes, but the vulnerable buffer only allowed 200 bytes. Rather than failing, the AI engineered a multi-packet bypass. It autonomously split the exploit into 6 sequential remote procedure call, RPC requests. Requests 1 through 5 carefully wrote the payload into memory piece by piece. The 6th request loaded the registers and triggered the execution. This level of strategic memory staging is the hallmark of an elite, nation-state hacker performed entirely by a machine. Here we visualize the FreeBSD payload constraint bypass. The AI generates a 1,000-byte ROP payload, but hits the 200-byte buffer limit decision node. It adapts by breaking the payload down. RPC request 1 stages the first chunk, and requests 2 through 5 stage the remainder. Once the memory is fully staged in the kernel, request 6 fires the execution trigger, resulting in unauthenticated root access over the network. To truly grasp the power behind these attacks, we must deep dive into the orchestration architecture known as VCAO, Verifier-Centered Agentic Orchestration. Mythos doesn't just read code blindly, it acts as a strategic general. VCAO formulates vulnerability discovery as a repeated Bayesian Stackelberg search game. The large reasoning model acts as the orchestrator, allocating analysis budgets across different kernel files and external tools like CodeQL, static analyzers, and traditional fuzzers. If a fuzzer returns a partial crash, the orchestrator performs a Bayesian belief update, dynamically redirecting its focus and budget to that specific kernel subsystem. By treating kernel auditing as a mathematically optimized wargame, it achieves 2.7 times more validated vulnerabilities than coverage-only fuzzing. It is a self-directing, self-optimizing cyber warfare engine. This flowchart maps the VCAO orchestration loop. The large reasoning model orchestrator allocates compute budget to specialized agents, CodeQL, fuzzing, and Kaizen. These agents test the kernel and feed their observation results back into the system. This triggers a Bayesian update, refining the orchestrator's strategy for the next loop. Confirmed flaws are passed to the cascaded verifier for final exploit generation. Let's look at a massive real-time use case, the security of the public cloud. Cloud providers rely on virtual machine monitors, or VMMs, to securely isolate customers sharing the same physical hardware. If an attacker escapes the guest VM and hits the host, they compromise everyone. Mythos audited a production VMM built in a memory-safe language. It identified that code interacting with hardware must eventually use raw pointers like Rust's unsafe keyword, and it found an out-of-bounds write vulnerability in that exact translation layer. Because this puts global infrastructure at risk, Anthropic refused to release Mythos publicly. Instead, they launched Project Glasswing, providing restricted access to cloud giants like AWS, Google, and Microsoft so they can use the AI defensively to patch these hypervisors before adversaries do. This diagram highlights the VMM threat model. A guest cloud workload attempts to escape via a VMM unsafe code block. Under Mythos analysis, a vulnerability is found. Left unchecked, this leads to guest-to-host memory corruption and total server compromise. However, through Project Glasswing, this discovery is routed to defensive AI patching, resulting in secured cloud infrastructure before attackers can strike. To conclude, the existence of Mythos-class agents proves that the window between vulnerability discovery and exploitation has collapsed to zero. Human speed triage is now completely obsolete. Organizations must transition to machine speed defense. You must shift left by integrating frontier AI models directly into your development pipelines, allowing the AI to break your code before it ever reaches production. You must implement continuous red teaming, using autonomous agents to constantly test your own zero-trust boundaries. The vulnerability tsunami is here, and you must fight AI with AI. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Thank you for joining this masterclass. Our final diagram outlines the pillars of machine speed defense. Organizations must implement automated AI patching, shift-left AI integration, continuous autonomous red teaming, and strict zero-trust architecture. All four of these dynamic defenses converge to create a resilient OS infrastructure capable of withstanding the relentless assaults of frontier AI models.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials, and click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our